Up to now, I finished the first part of my lecture. We should take something like break 10 minutes or something like that if we have a question or something like this.
Yes. So, anyone has a question?
Yes, sir.
Yes.
Thank you for your today's lecture. And could you back to page 11?
11.
Yeah.
11. Yes. This one. Okay.
And I would like to know why delta pi equals 0 means the sigma ijj equals 0.
Okay. Why delta pi is equal to 0? Okay. I don't want to explain this now, but as far as I'm looking for white. Okay. This is, we should explain this one when we talk about the variational formulation. As far as I am asked, okay, if I want to ask a very simple question, how can I prove that the distance, how can I prove that the distance, the minimum distance between 2 points are a straight line? Can we prove something like this? It is impossible. It is impossible to prove that the distance between two lines are the straight line using the traditional calculus of differentiation and integration. It is impossible. Okay? Because of that, we started to invent another way of calculus called calculus of variation, of variational calculus. Okay? The idea is very simple. It choose any path. Each path you are going to choose your function. So this function is arbitrary function. Okay. Each function is associated with the distance. So the distance here, it is called the functional. Okay. Functional. It is function and AL. The AL comes from real. So there is a value, real value is associated with each function. Because of that, we call it d of f. So when you change f, or actually it is d of f of x. So it is function of function, but it is not a composite function. Because the composite function, you will end up to another function. Okay? Okay? But this one is, each function is associated with number, with real number. Okay? So when we minimize this distance, we carry out operation called delta. D equal to 0. That means we minimize the distance. When we carry out this, we will end up to the solution f equal ax plus b. Okay, how? Using Euler-Lagrange equation. I promise I will give full lecture about this. Okay, how to start from this problem until we reach the equilibrium. In mechanics, we find that when we compute strain energy, there is something called the strain energy. Strain energy. This strain energy has nothing to do with equilibrium. But if we subtract the work done by external of this strain energy is the integral over the domain sigma ij times epsilon ij 1/2. Okay? So it is actually in one dimension is the area under curve from epsilon and the sigma. This is the area under curve. 1/2 times the stress and the strain. In multi-dimension, it is functional. This is functional because it depended on the displacement and traction and the epsilon, the strain and the stresses. Okay, this has nothing to do with equilibrium, but we find when we subtract the work done by the traction on the boundary times the displacement on the boundary, this is a new value, we call it pi. In mechanics, they call it the total potential energy. Okay, and from the word total, they said that these two is the work done by external force. So it is actually E plus minus Ti Ui. If you can see, it is all dummy indices. We find that when this new functional by, when it is minimum, like when we have a straight line, this is corresponding to the equilibrium. This is corresponding to equilibrium. This is corresponding to, this is from the principle of the least action. Let us give full problem, full lecture on explaining this one. The one who did this geometrically, it was Euler, and his student Lagrange, he did it using Euler-Lagrange equation. It's very, very elegant equation. And after that, if you remember, Hamilton got this equation using Legendre transform and break it down, instead of having a strong form to two weak forms, and this is called the Hamiltonian mechanics. Newtonian mechanics, together with the Lagrange equation, together with Hamilton equation, this is called the classical mechanics. Okay? So actually, the initial problem, it was started at, I think, the 16 something is not the 15th century of the 16th century. I'm not to remember actually when it was not the minimum distance between 2 points. It was called the Parakistochrone problem. If you remember this Parakistochrone problem, they were asking, we need a curve here when we place a ball here and it rolls, it will reach the bottom of the surface using the minimum time. Time is minimum. And it was fine, this line is a cycloid. If you remember, it's a cycloid curve or something like this. This is called Parakistochrone problem, and it was the original problem that starts the calculus of variation, actually. Okay? This is outlines we need to be honest, we need one lecture to demonstrate how to reach how to understand the perturbation, how to understand the minimum potential energy, because all is very, very, very nice. It's very difficult to reply this in 5 minutes or something like that. So excuse me, just give me after 2 or 3 lectures, I will come back to this point in details. And I'll show that both boundary elements and finite elements has the same origin. Actually, if we have 5 or 6 steps, the same 5 steps, the last step only. This one, they use polynomial, and in our case, we use the fundamental solution. And Professor Xinghua Xin has a fantastic actually breakthrough in doing these variational-based finite elements. Variational-based boundary elements or fundamental solution-based boundary elements. Okay, so just allow me 2 more lectures, actually 3 more lectures. One for continuous of a quadratic element, one for the fundamental solution, how to derive fundamental solution, one for transformation domain integral to the boundary. Then we will come back again to this variational formulation. Okay.
Thank you again, Professor.
Okay. Yeah, so
shall we take the,
so maybe we have 10 minutes
okay,
break.
10 minutes.
Yeah, see you soon.
See you. Bye.